So last time around, we reviewed the idea of induction. And we looked at induction on the natural numbers, and we looked at induction on the type of lists in Haskell. We gave a number of examples of inductive proofs, and we also emphasized the process of how you actually produce these kind of proofs. So I gave you a range of hints and tips for how to construct inductive proofs. So what we're going to be looking at today is using induction to actually construct or to write programs, not just about proving properties about programs. And this is really like a secret trick which is actually not that well known. So the background to today's class is that many functions are naturally defined using the ++ or append operator on lists. But as we'll see, the resulting functions can often be inefficient when the append or ++ operator is used recursively. So what we're going to see today is how induction can be used to eliminate the append operator or to make it vanish, as shown in my badly drawn picture here on the slide, and hence improve the efficiency of your programs. So this is what we're going to be looking at today, how to use induction to make append vanish. So as we often do with these things, we're going to come at the problem by means of a simple example. So let me first of all refresh your memory about how you define the append operator, which is written as ++ in Haskell. And it's got a very simple type. It simply takes a list of A and another list of A, and then it's going to combine them into a single list of A by just appending the two lists together. And it's got a very simple two-line recursive definition. In the base case, we simply say if you take the empty list and you append it to any other list y's, then you're simply going to get back the list y's. And in the recursive case, if you take a non-empty list, x followed by x's, and you append it onto any other list y's, then all you're going to do is you simply output the first value in the first list, x, and then you're going to recursively continue by appending x's to y's. So a very nice, simple two-line recursive definition for the append function. Well, what can we actually do with the append function? Well, the example that we're going to consider here is the function called reverse from the standard library. And of course, reverse simply takes a list of A's and is going to give you back a list of A's. And it's also defined recursively, and the crucial point here is that it's defined recursively in terms of the append operator. So the base case is very simple. If you reverse a list with nothing in it, you get a list with nothing in it. And the recursive case, which is the interesting one, says if you reverse a non-empty list where x is the first thing and x's is everything else, then all you're going to do is you're going to reverse the tail of the list, x's, and then you're going to append the singleton list with x in it on at the end. So the important point here is that reverse is a recursive function, and it's defined recursively, and it involves the use of the append operator. So the question that we want to ask ourselves now is how efficient is this recursive definition for reverse, which uses the append operator? And actually, we're going to begin with a simpler question: how efficient is the append operator itself? So we can make this precise. We can say how many evaluation steps does an arbitrary append take? So an arbitrary append would just be x's ++ y's. So this is the first question we're going to answer. How many evaluation steps does x's ++ y's take? And in order to make this simple, we're going to assume that the two argument lists, x's and y's, are already fully evaluated before the append operator is applied. So we don't need to worry about also taking account of the number of steps that these evaluations take. All we're going to worry about is how many evaluation steps does the actual plus plus operator itself take. So we'll assume x's and y's are already fully evaluated. So in order to answer this question, we're just going to have a simple example. Let me make a bit of space for the example. And the example we're going to look at is simply, we're going to take x's to be the list 1, 2, and then we're going to take y's to be the list with a single 3 in it. And then all we're going to do now is apply the recursive definition for the append operator and work out how many evaluation steps this actually takes. So the first step is very straightforward because the first input list is non-empty. So we apply the recursive case and we'll output the first value, which is 1. And then we'll have the remaining list in the first list, which is the 2 plus 3. Okay, so that's just unwinding the recursive definition one step. Then we can look to the part inside the brackets here, and again we still have a non-empty list appended to something, so we apply the recursive case one more time. So we'll get 1 colon, and then we'll get a 2 colon, and then in brackets we now have the empty list left as the first argument, and then we simply copy down the plus 3 again. And finally now, inside the brackets here, we have reached the point where the base case applies because we have the empty list appended to something. So if we apply the base case now, we're simply going to get the 1 and then the 2, and then we'll simply output the list 3. Okay, so we're now done, and this is our final result, and this is just a kind of internal way in Haskell using the colon operator of writing the list 1, 2, 3, which is exactly what we expect from appending the two argument lists. So now that we've completed the evaluation, we can look at this and think, how many evaluation steps did it actually take? And all we need to do is count the equal signs. So we have 1, 2, and 3. So this particular evaluation took 3 evaluation steps. And then you can ask yourself, why did it take 3 steps? Well, it's to do with how the plus plus operator is defined. It's defined by recursion on its first parameter, which in this case is the list 1, 2. And this list has 2 elements, and the reason why we end up with 3 evaluation steps is we have 1 evaluation step for each of the 2 elements in the list, and then we have a final evaluation step for the empty list at the end, so that's why we end up with 3 evaluation steps. So in conclusion, if I have an arbitrary append, x's plus y's, based on this example, we can say that x's plus y's is going to take the length of the first list, length of x's, plus 1 evaluation steps. Okay, so just based on this simple example, this is what we worked out. X's plus y's takes the length of the first list plus 1 steps. So in our particular example, the first list had 2 elements, so we take its length, which is 2, and then you add 1 and we get 3, and that's why we get these 3 steps here. So if you wanted to be a bit more fancy about this, what this means in yellow is that x's plus y's takes linear time in the length of the first argument list x's, which is quite an efficient function. So now that we've worked out the efficiency of the append operator, we can go back to our main question, which is how efficient is the reverse function itself. So again, we can start off by making this question precise. We can write it down in English. So what we want to know is how many evaluation steps does an arbitrary reverse take? So we'll take reverse of x's. How many steps does this take? So again, we're going to come at this by means of a simple example. So again, let me just write this out, or rub it out. And we're going to consider this time, we're going to reverse the list with 1 and 2 in it. And all we'll do again is unwind the recursive definition for reverse and then see how many evaluation steps this actually takes. So if we apply the definition of reverse, we have a non-empty list. So what we can do in the first step is we're simply going to reverse the tail of the list, which is 2, and then we're going to stick the 1 on at the end. So nice and simple, just unwinding the recursive definition one step. Then again, we go to the definition of reverse. We know how to reverse non-empty lists, so we apply the recursive definition one more time. So this time we would reverse the tail of the list, which is now empty. Then we'd stick the 2 on the end, and then we still need to remember to copy down the ++1. And now inside the brackets here, we've reached the point where we have the base case for the recursive definition for reverse. So we know how to reverse an empty list. That's simply the empty list. So in the line here, we can say we have the empty list ++, 2, and then ++1. Okay, so at this point now, we can think how many evaluation steps is this actually going to take to evaluate to completion. So if we think about what we've got here, to get to the point where the recursion for reverse has stopped, we took 3 steps. Okay, so we can count these steps over here. We just count the equal signs. We took 3 steps to get to the point where we'd eliminated the definition for reverse, and all we have left now to compute is the result of doing these 2 appends. And to get to this point took 3 evaluation steps. But then of course we need to remember that we still need to evaluate this append and that append. But we just worked out the efficiency of append, so we know how many steps this is going to take. If we look at the first one here, the first list here has no elements, and remember x's plus y's takes the length of x's plus 1 steps. So in this case we have a list with nothing in it, so doing that append is going to take 1 step. Okay, and then we can think, how do we do this append here? So it's the same game again. We're going to compute how many steps it's going to take. So the result of this append, this is going to give a list with 1 value in it. So when you append a list with 1 value in it to anything else, it's going to take 2 steps. Because remember, append always takes 1 more step than the length of its first argument. So the conclusion here is that this append, the outer append, is going to take 2 steps. Okay, so you see, for this particular example, when we're reversing a list with 2 elements, it takes 3 steps to eliminate the use of the reverse operator. So we get down to the point where all we have to do is appends, and then it took 1 step for the first append, and then 2 steps for the second append. Okay, so we can draw a conclusion from this now, which is a very simple conclusion. So the conclusion here is, in general, reverse of x's. If you take an arbitrary list x's, the number of steps it's going to take is, if you kind of expand from this particular example, so when we had the list 1, 2, it was going to take 3 steps to eliminate the use of reverse, and then 1 step to do the first append and 2 steps for the second append. So in general, what you can see is what you're going to have is it's going to take 1 plus 2 plus ... plus n plus 1 steps where n is simply the length of the list. So what we saw in our example, we were reversing the list 1, 2, which has 2 elements. So when you take its length, n is going to be 2. So when we compute the sum, we just do 1 plus 2 plus 3. But this here captures the general case. If you want to compute recursive x's, it's going to take this sum here, 1 plus 2, all the way up to n plus 1 number of steps, where n is simply the length of x's. So what we can do now is look at a summation, such as this one, and ask ourselves, how do we actually work out what the result of that is? What's the result of a summation of this form? And actually what we can do here is go back to something which hopefully you learned about in school, and it's how you compute the result of an arbitrary summation of this form. So let's have a simple example of this. So suppose we were computing the result of 1 plus 2 plus 3 plus 4 plus 5. And in this case, we only have 5 numbers, so it's very easy to add it up in your head, and you see that the result is 15. But what we want is a general formula for computing these kind of summations. And the trick to coming up with this formula is that you could add up the numbers in any old order that you like, because addition is commutative. So for example, I could add them up in reverse order. I could take 5 plus 4 plus 3 plus 2 plus 1. And because addition is commutative, I will of course get the same result. And then you can think, well, why does this help me at all? Well, it helps me because if I look at the columns here, each of these adds up to 6. So 1 plus 5 is 6, 2 plus 4 is 6, and so on and so on. So if I imagine taking the sum of these two sequences in column form, so if I take the sum of 1 and 5, I get 6, the sum of 2 and 4 is 6, and so on. So what I'm going to get down here is 6 plus 6 plus 6, and so on. And then of course, when I sum these two final values over here, I'm going to get twice the answer which I'm looking for, which is 30. So you can look at this now and think, why does this actually help me to calculate that the sum of the first 5 numbers is 15? Well, if you look to see what we've got now, we've got this summation of 5 6s. So this is really like 5 times 6, which is 30. Okay, so this is giving you a simple trick to work out what the summation is. If I wanted to sum the numbers from 1 to 5, all I'm going to do is multiply 5 by 6. That's what we've got in yellow at the bottom here. That will give me the 30, and then I halve that and I get the 15. Okay, so this is a little trick for computing a sum such as this one. So the general case is, so I'm computing a summation, and I'm going from I equals 1 up to whatever n is, and then I'm summing over the values I. So I'm going from I equals 1 up to some arbitrary value n, which could be 5, for example, and I'm summing each of these things. And what you see from this example above is, in order to compute that result, all you're going to do is take your number n, like 5, multiply it by the successor, like 6, and then you're going to divide it by 2. So that's all we were doing up here. We're taking our number, which was 5, and we're multiplying it by 6. So 5 times 6 is 30. So that's what we'll get down here. And then we divide it by 2, and that will give us back the result 15, which we actually want. And there's a nice story about this formula. History tells us, or maybe tells us, that this formula was discovered by Carl Gauss, a mathematician, when he was 7 years old. And the story is that his teacher in his school was wanting the class to shut up for a while. So the teacher said, please work out what is the sum of the first 100 integers. And Gauss essentially came up with this formula, and he immediately could tell that the result was 5050. Now that we've reviewed Gauss's magic formula, we can think, how does it apply to our particular example? So what we're doing here is we're calculating the sum of the numbers between 1 and n plus 1. And what Gauss's formula tells us is how to do that by plugging n plus 1 into the formula. So if we plug in n plus 1, what we're going to get back is n plus 1 times the successor of that, which is n plus 2, and then we divide everything by 2. And this tells us what the result of that summation is. So we can actually simplify things a bit further. If we look on the top line here, we have n plus 1 times n plus 2. And in school, we learn how to multiply out brackets like that. So we could multiply out those brackets. And what we'll get is n squared plus 3n plus 2. So what we have now is our final precise formula for how many steps it takes to evaluate a reverse. And in particular, if we have an input list x's and it has length n, then it's going to take n squared plus 3n plus 2 divided by 2 steps to perform that reversal. And you can ask yourself, is this an efficient function or is it not? And the answer is it's not an efficient function because we have a squaring term here. And what this is telling us is that the reverse function takes quadratic time in the length of its argument. And quadratic time algorithms are typically bad. So for example, if you took a list with 10,000 elements in it and you reversed it using the recursive definition for reverse in terms of append, you'd find if you plug it into this formula that it's going to take about 50 million evaluation steps, which is way too many. And again, it's taking way too many evaluation steps because the recursive definition for reverse using append actually ends up taking quadratic time, which is bad. This now brings us to the main question of this lecture. How can we eliminate the use of append or make the append vanish from the definition of the reverse function and thereby make it more efficient? And it turns out there's a really simple trick here, and the trick is we're first going to define a more general function that combines the behavior of reverse and append. So let me give you a specification for the function that we'd like to define. So I'd like to define a new function called reverse prime. So it's not the same as the reverse function, and it's going to take two input lists, x's and y's, and it's going to combine the behavior of reverse and plus plus by doing a bit of reversing and a bit of plus plussing. So what does this mean in practice? Well, what I'd like it to do is I'd like it to reverse the first list, and then it's going to append the second list on the end. And let me put some brackets in here to make clear precisely what I mean. So this is something I'm going to come back to a number of times. So let me put it in a little red box, like I sometimes do with the important things. So what we have here now is we have a specification for the function reverse prime, which we would like to define. So I'm going to regard this equation as being something that we want to solve. It's got an unknown. We don't know what the definition of reverse prime is, but what we would like it to do is it would have the same effect as reversing its first parameter and then appending the second parameter on the end. So again, I'm not regarding this as being a definition for the reverse prime function. I'm thinking of this as being an equation that we want to now solve, and we'd like to solve it by giving a definition for the reverse prime function which doesn't refer to either the original definition of the reverse function or the original definition for the plus plus function. So this is the name of the game. We would like to try and construct a function called reverse prime, which combines the behavior of reverse and append by satisfying this simple equation here. So a couple of points to note before we move on. So this is a specification for the function, and we would like to find an implementation. We'd like to solve this equation by coming up with a recursive definition for reverse. And the way I'm going to do this is by what's called constructive induction. So what many people would do at this point is they would just give you a recursive definition for this function and then prove that it satisfies this specification. That's not what I'm going to do. I'm going to try and prove that this equation is true by induction on the argument x's, even though I don't yet know what the definition for reverse prime is. And what we'll find by this process of what's called constructive induction is that we get the definition for the reverse prime function essentially for free by following the induction process. So let's see how this actually works out in practice. So we'll do the base case first of all. So let me write down base case here. So what we're going to do is take our equation here and we're going to attempt to prove that it's true when the input list x's is empty. And what we'll find is that even though we don't know what the definition for the reverse prime function is yet, we know that it has to satisfy this specification, and by applying the process of constructive induction, we'll actually get the base case arising for free. So how does this actually work in practice? So what we're going to do is we'll take our left-hand side, which is reverse prime, and the input list x's is going to be the empty list, and then we have the list y's, and then we think, well, what can we do? Well, the only thing that we know about the reverse prime function is that it must satisfy this equation here. So if we were to apply our specification, this would allow us to rewrite this as reverse of the empty list, let me put the brackets in here, plus plus y's. So just by applying the specification, I could get down to this point. Then you think, well, what could I do? Well, it's very easy to simplify in the brackets here. I know how to reverse the empty list. By definition, that is simply the empty list. So if I apply the definition of reverse, I get the empty list, and then I copy down the plus plus y's. And then I think, well, what can I do now? Well, I know how to append the empty list to anything because the definition for append tells me what to do. So if I simply apply the definition for the append operator, I will get down to y's here. And if you think, what's actually happened here is I have shown that this is equal to this. And actually this gives me the definition for the reverse prime function in the base case. So what I have actually done is I have calculated, using equational reasoning, what the recursive or the base case for the recursive definition for the reverse prime function should be. It's simply this. So all I've done is read this off. Reverse prime of the empty list applied to y's. By a three-step calculation, I got down to y's, and this actually gives me my base case for my recursive definition. And it's interesting to think, well, what's actually gone on here? If I gave you the definition of the base case in yellow and asked you to prove that it satisfies this property in the base case, you would essentially do the same steps as I did in my calculation here, but just in a slightly different order. And the interesting thing here is I didn't need to give you the definition in yellow. I calculated it just by applying the simple equational reasoning, which we've been doing. Now we can play exactly the same game with the inductive case. So what we're going to do is exactly the same as we did in the base case, except now we're trying to calculate the definition in the non-empty list case. So this time we're working with reverse prime, and we no longer have the empty list now. Now we have a non-empty list, x followed by x's, and we have an arbitrary second list y's, and we simply want to calculate using equational reasoning, using the process of constructive induction, and what we'll find is that this will give us the definition of reverse prime in the recursive case. So what can we do? Well, if we look at what we've got here, again, the only thing we know about the reverse prime function is that it's going to satisfy, or it has to satisfy, this specification here. So just like in the base case, in the first step, we can simply rewrite this, and let me move this down a little bit. We're going to say we get reverse of x followed by x's, and then plus plus y's. So all I have done in the first step here is applied my specification. Then I can look at the expression which I have and think, what can I do? Well, I can expand or apply the definition of the reverse function, because I know how to reverse a non-empty list. So if I simply apply the definition of reverse, what I'm going to get is reverse of the tail of the list plus plus the first thing sitting in a little list on its own, and then I'll copy down the y's here. Now I can look at this expression and think, what should I do with it, or what could I do with it? And actually, this is one of these points where there's a bit of kind of style advice here, or some hints and tips. When you have repeated use of append and it's bracketed one way, in this case it's bracketed to the left, we have two appends bracketed to the left, it's almost always a good idea when you're doing these kind of equation or reasoning calculations to re-bracket it by exploiting the fact that append is associative. So if you have three lists, x, y's and z's, and you append them, it doesn't matter whether you bracket them to the left or you bracket them to the right, you will get the same result. So let me re-bracket by exploiting the fact that append is associative. So I'll get reverse of x's, and then I'm going to bracket to the right this time around. So I'll get x sitting in a little list, appended with y's, and now I think, what can I do? Well, you can see now why it was a good idea to re-bracket, because this is something which I can now simplify. If I was to apply the definition of append at this point to a singleton list comprising the value x, and then I'm appending the list y's on the end, that is simply going to be x colon y's. So I could simplify this. I copy down the reverse of x's, and what I have in the brackets now is x colon y's. That's simply applying the definition of plus plus. So now I can look at this expression and think, well, what can I actually do? And I can't apply the definition of reverse at this point because I don't know anything about the list. It's just reversing of an arbitrary list x's. And I can't do anything with the plus plus either because I don't know whether I've got a non-empty list or an empty list as the first argument. So I seem to be a bit stuck. But at this point, I remember that I'm doing an inductive proof or an inductive calculation. So in particular, I'm allowed to assume that the property which I'm trying to prove is already true for any argument list x's and any argument list y's. And if you look at this part here, this is exactly what we have in our calculation. So if you look back to the calculation, what we have here is we've got reverse of x's appended with some other list. So by induction, we're allowed to assume that this list here is the same as this. Okay, so by applying induction, what I can do is I can replace the last line here by reverse prime of x's, oops, I can't spell, reverse prime of x's, and then x colon y's. So again, in the final step here, all I did is I applied my induction hypothesis, which allows me to conclude inductively that this is the same as this. And actually, this now completes our calculation. What we've actually done by the process of constructive induction is we have shown that this expression here is the same as this expression here. And just as in the base case, this actually gives us the definition for the reverse prime function, this time in the recursive case. So if I just copy this down now, what I have actually done is calculated that reverse prime of a non-empty list, x colon x's, and then some other list y's is going to be, and all I do is copy down what I got in the end here, which is simply reverse prime, x's, and then x colon y's. And again, I didn't need to know that this was the recursive definition for reverse prime applied to a non-empty list. I got this for free just by applying this process of constructive induction, starting from this specification here. So I've ended up with the two cases now. I have the base case for the recursive definition for reverse prime down the bottom here, and I have the recursive case for the definition of reverse prime down the bottom of the slide here. To wrap things up now, what we can do is write down the final definition for the recursive function that we have calculated. So what we have done is we've calculated a recursive function called reverse prime, and it takes two lists and gives back a single list. And the recursive definition which we have calculated using the process of constructive induction has a base case, which we'll define, and it has a recursive case as well, x colon x's, and then a list y's. And what we found is that by the process of constructive induction, in the base case, we simply return the list y's. And in the recursive case, we call ourselves recursively, we call reverse prime, and we call it on the tail of the first input list, so that's x's, and then we put x onto the start of the second argument, y's. And the important thing here is that reverse prime, by construction, satisfies this equation here. So reverse prime x's and y's will be guaranteed to reverse x's and then append y's on the end, because we constructed it to satisfy this specification. But the interesting thing now is when you look at the final definition of the reverse prime function, it doesn't use append and it doesn't use reverse. It's just a straightforward recursive definition in terms of itself. But then you can ask yourself, well, it's not reverse prime that we're actually interested in. We wanted to have a more efficient version of the reverse function. But it's actually very simple now to recover the reverse function in terms of reverse prime. So I'm going to define a new version of reverse. It's got the same type as the original one. It takes a list and gives back a list. And how am I going to define this? Well, I'll give it a list, and then I'm going to call reverse prime, and I'm going to pass in x's as the first parameter, and I'm going to pass in the empty list as the second parameter. And why is this the right thing to do? Why does this give us the behavior of the original reverse function? And again, if we look back to our specification here, what happens with the second argument is that's being appended on the end. That's the behavior of the reverse prime function. So if we pass in the empty list as the y's parameter, that's going to append the empty list on to the result of reversing the list x's, which will of course have no effect. If you append an empty list onto any list, it has no effect and you'll just get back the original list. So what this is telling us is if we pass in a list x's and we pass in the empty list, then what this will give you is the effect of just reversing the list, because appending the empty list afterwards doesn't actually do anything. So if we go back to our final definition now, here is our final definition for the reverse function in terms of this function called reverse prime, which we calculated by the process of constructive induction. So what we can do now is we can do a little example of this. So we could try what's going to happen now if we reverse a list such as 1, 2, 3. So what's going to happen is we will go to our definition of reverse, which says if you want to reverse a list, now you just call reverse prime and you pass in the list and you pass in the empty list. So we can do that. So we can say you get reverse prime, and then 1, 2, 3, and then you get the empty list. And now what do? Well, we just apply the definition of reverse prime. And what does that say? Well, if you reverse prime something, all you're going to do is apply this case here. So what we will do is we will match on the non-empty list, and we will call ourselves recursively, and we'll put the first value onto the start of the second list. So we can just see how that actually works out in practice with this example. So if we apply the reverse prime function, all we're going to do is we'll get left with the 2, 3 here, and we'll put the 1 onto the start of the second list. And then we just continue with this process. You reverse prime, you will remove the first value, and you will put it onto the start of the second list. And then we do the same one more time. So we reverse prime, we get the empty list here, and we put the first thing on the start of that list. And now we have reached the point where the base case applies, because we have the empty list here. And in the base case, when we look at the definition, when you have the empty list, all you do is you copy across the second list, and then you are done. So in this case, all we're going to do is copy across the second list, which is 3, 2, 1, and then we are done. So what we see now is that we've reversed the list 1, 2, 3 to get the list 3, 2, 1, and we can count how many steps it's taken. It's taken 1, 2, 3, 4, 5 steps this time around. And it's also worth kind of having a think before we just reflect on the complexity or the time complexity of this new definition. What's actually going on with the new definition of the reverse function? And the trick here is that we're really using this second parameter as what's called an accumulator. It's being used to accumulate the result of reversing the list x's. So initially our accumulator is the empty list because we haven't accumulated any reversed elements. And then what we do in the recursive case is we match on the first list, and then we have our accumulator, and all we're going to do is recurse with the tail of the list, and then we put the first value in the first list on to the accumulator. Okay, so this is how this function is actually achieving the result of reversing the list. So what I think you'd agree is that this definition for reverse, we have this top level definition, and then we have this helper function here, which is actually doing the work. This is less clear than the original definition of reverse, but it's much more efficient because it doesn't use the append operator. And again, the interesting idea here is that we've arrived at the definition for the reverse prime function, this one here, by the process of constructive induction. We didn't know what the definition of this function should be. We arrived at it by postulating the existence of a function called reverse prime, which did a bit of reversing and a bit of appending. We calculated a definition for that function, and then we saw how you could recover the behavior of the original reverse function from it. And just to wrap things up finally, just kind of generalizing from this example here, what we can conclude, just write this on a new page, is that with this new definition, reverse x's now takes length of x's plus 2 steps. Okay, so in our particular example, we had a list with 3 elements, 1, 2, 3, and it took 5 steps to get down to the list 3, 2, 1. And it's very easy to see that this is the general pattern. If your list has n elements, then it's going to take n plus 2 elements to perform the reversal. So this is now an efficient function. Previously, the definition of reverse using append took quadratic time. This is now a linear time function, so it's much more efficient. And again, the point is that we arrived at this definition by making the append operator vanish using the idea of constructive induction. So that's it for today. I'll see you again next time.